Welcome to this explainer. Before a single spark flies from a welder's torch or a single piece of steel is actually cut, a massive ocean vessel must exist entirely in someone's mind. That is ship design. And let me tell you, it is far, far more complex than just drawing a boat. Today, we're exploring the incredible engineering journey that transforms a blank screen and raw data into a literal floating city. So grab your hard hats, because we are diving deep into the blueprint of the sea. Think about it. How exactly do you turn a napkin sketch into a 300-meter Leviathan? We are talking about structures longer than 3 football fields, hauling 80,000 tons of iron ore, and built to survive the absolute harshest environments on Earth for 25 years. The sheer scale is just mind-blowing, right? Moving from that blank screen to a finished tanker requires this immense, almost magical level of engineering discipline. It's a journey that has to dictate absolutely every physical and performance characteristic way before construction even begins. To really grasp this, we need to contrast it with something familiar. If you're designing a static building, say a house or a skyscraper, it sits on dirt. The variables are mostly independent. Want a bigger living room? Well, you just push a wall out. Easy. But a ship operates in a dynamic, incredibly unpredictable ocean environment. Everything is interconnected. You just can't optimize one single element in isolation. If you try to make a quick structural change on a ship like you would a house, you trigger a massive chain reaction. Let's say the owner says, hey, I want to carry more cargo. Okay, more cargo means a heavier ship. A heavier ship means you need more power to push it through the water at the required speed. More power? Well, now the engine has to grow, which changes the ship's displacement, forcing the physical shape of the hull to change just to fit inside. And changing the hull shape, that completely alters the stability of the entire vessel. It's literally a massive interconnected spiderweb. Pulling on one single thread tugs at absolutely everything else. Section 1. The 3 stages of design. Taming the chaos. To actually pull this off and tame that chaos, ship design moves through 3 distinct, increasingly rigorous stages over time. You start with concept design in the first couple of months, followed by preliminary design, and finally, contract design. Think of each stage as a strict quality gate. And here is the absolutely crucial point. You cannot skip a stage. If you skip one, you are pretty much guaranteed to build the wrong ship. Let's break down exactly what happens at each of these stops. Concept design? That's all about the broad strokes. The owner basically says, I need to carry this much cargo at 14 knots. The naval architect runs some rough estimates to answer one simple question. Is this even feasible? Next up is preliminary design. This is where the engineering begins in earnest. We get the precise mathematical shape of the underwater body, the hull form. We run hydrostatic calculations to prove, that it actually floats, and power calculations to size up the engine. Finally, we reach contract design. This is the finished article. Every single system is defined, every pipe is routed, and every structural member is sized. This becomes the locked-down legal blueprint that the shipyard actually uses to start cutting steel. Section 2. The cost of change. Why stages exist. Now, why are those stages so rigid? Because of this exponential cost curve. It is the absolute nightmare of every shipyard manager. Look, if you make a mistake or change your mind early on in the concept stage, it costs almost nothing. You literally just erase a pencil sketch or delete a file. But try making that exact same change after the steel is already being cut and welded on the slipway. You're suddenly talking about millions of dollars in wasted materials and months of devastating delays. So those 3 design stages we just discussed, they exist purely to catch mistakes early, when they're still cheap to fix. Section 3. The design spiral, an elegant framework. Remember how we said everything depends on everything else? Because of that, there's no obvious place to start. So the naval architect just takes an educated first guess at the dimensions. From those dimensions, they sketch an arrangement, which gives them a guess at the mass. That mass tells them how much power they need. Then they calculate stability. Does the ship actually stay upright? Finally, they check the cost. And then? Well, they take everything they just learned, go all the way back to step 1, revise their initial guess, and go around the spiral again, over and over. With each revolution of this spiral, this really beautiful thing happens. Convergence. The numbers start to tighten. On loop 1, the dimension guess might be 185 meters. On loop 2, it drops to 183 meters. Loop 3, it lands at 183.5 meters. And when they round the spiral a 4th time and the math stays locked at exactly 183.5, boom, you've converged. The math has perfectly stabilized. You've found the exact solution that satisfies all those complex constraints simultaneously. There's a famous saying in maritime engineering, the owner does not want the biggest ship, They want the most profitable ship. Frankly, any shipyard can build a massive, over-engineered hunk of steel. But the design spiral forces the architect to find the minimum ship that does the job safely and effectively. It perfectly balances safety, performance, and cost to find the absolute most economically efficient solution out there.
Section 4. The Digital Twin, CAD and CAM.
All of this brings us to the digital revolution. CAD, or computer-aided design, is how the entire ship is engineered and drawn in a 3D digital space. CAM, computer-aided manufacturing, is how those digital designs are sent directly to the massive machines on the shop floor that actually cut and bend the steel. The true power here is the flawless link between the two. You draw a part exactly once in the computer, and the machine cuts it perfectly in the real world. No human transcription errors, no misread, coffee-stained blueprints.
This leads to some incredibly smart manufacturing techniques, like nesting. The software basically takes hundreds of individual part shapes and automatically arranges them onto standard flat steel plates, like a giant high-stakes game of Tetris. We're talking about 94% of the raw steel being utilized, with only a tiny fraction left over as minimal off-cut waste. Just a 5% improvement in this nesting process across a massive cargo ship saves hundreds of tons of raw steel. Without computers, this used to take days of manual work, with way worse results.
All of this digital work culminates in what's called the ship product model. Today, a ship is actually built twice, first in a computer and then in steel. The ship product model is this massive, fully integrated 3D database. If you could zoom in and look inside it, you'd see every single pipe, every cable tray, every steel plate, and every ventilation duct, all completely modeled and connected in virtual space before a single spark ever flies in the physical shipyard.
This master model acts as the brain for the entire shipyard. From this single 3D database, the yard automatically generates the numerical control cutting programs for the lasers, the block assembly drawings for the workers, the material procurement lists, and even the exact weight estimates for the final stability checks. So the really crucial point is this. If an engineer changes just one pipe routing in the 3D model, all of those downstream manufacturing outputs update automatically. It's just a flawless stream of information from imagination straight to reality.
So let's wrap this up. Ship design is a discipline where absolutely every parameter is linked. Change one thing and you change everything. We've seen how this chaos is brought to order through 3 strict design stages: the elegant math of the design spiral and the flawless integration of a digital twin. If a 300-meter floating city of steel must first be built entirely in data and imagination, what are the actual limits to what we can build next? Thank you so much for joining me on this explainer. Be sure to subscribe and hit the bell, and I'll see you next time for our next episode, The 3 Stages of Ship Design, explained from scratch.